What temperature does water boil at? Seems like the right answer is 100 degrees Celsius. But that's not true everywhere. Water's boiling point can differ at different elevations. So at sea level, that's the familiar 100 degrees Celsius. When you move to higher elevation, you can see that the water's boiling temperature is decreasing. And if you look at below sea level, elevation that's below sea level experiences a boiling point for water that's higher than 100 degrees Celsius, and it increases the further down you go. It's not so much the elevation or how high you are that determines the boiling point of water or the boiling point of anything. It's the pressure, the atmospheric pressure on the high elevations is less. There is more pressure on you, more atmospheric pressure, the lower you go. The column of air above you is larger, and so you have a higher pressure on you. We'll be looking at boiling and other phase transitions using a phase diagram. Here we have a phase diagram for water. It consists of three curves. They divide the diagram into regions labeled solid, liquid, and gas. In each region, the indicated state is stable. At every point of each of the curves, we have our boiling points, our melting points, the sublimation curve. That's the boundary between solid and gas. So if you think of dry ice goes from solid straight into a gas. The line is an equilibrium. We'll get into more about the phase diagrams after we do a little recap of the different states of matter. Solid state. In a solid state, particles are tightly packed. They can have a crystalline structure, an organized repeating pattern, or it could be like glass, amorphic, where you have a little bit more disorder there. But those particles are tightly packed as well. As temperature changes, a solid can expand. It could also contract. Solids have strong intermolecular forces that keep the particles close to each other. Solids exist under high pressure They also can exist at low temperatures. When pressure increases, or the solid is heated, a solid can melt to form a liquid or sublime to become a gas, as intermolecular forces are broken between the particles. So here we have a liquid. Take any point here. That liquid is at a specific temperature. If we're dealing with water, let's say its temperature is 10 degrees Celsius. If we keep it at the same pressure, we're not changing pressure, but lower the temperature, we can bring it from liquid to solid. That means that it is freezing. So you can bring a liquid to a solid region by lowering the temperature. If you also increase the pressure, so let's say we're right here, we increase the pressure, that would work too at the same temperature, just increasing pressure high enough. Solids could also sublime if we have a given temperature and we reduce the pressure dramatically. For some substances, it might not be possible at a given temperature to just reduce pressure alone in order to go through sublimation. So if we're at this specific temperature and pressure and we start reducing the pressure, you can see you have to go through this melting curve. You have to melt before you can become a gas. Liquid states. In a liquid state, particles can freely move within the boundary of the container the liquid is in. There are some intermolecular forces between them that hold them in a liquid state. If pressure is increased or temperature is decreased, particles are forced closer to each other, or particles slow down. They have less kinetic energy, causing a liquid to freeze into a solid. If pressure is decreased or temperature is increased, particles may move further apart or speed up, causing the liquid to boil into a gas. So there are two boundaries here with the liquid. Our boiling curve. So if temperature is increased, that means that we could move this direction where a liquid crosses that boundary. It becomes in equilibrium with the gas until it is moved completely into a gas phase. Pressure can be decreased as well. So you can move at a specific temperature, decrease the pressure, and then boil your gas. Gaseous state. In a gaseous state, particles can move freely with no definite shape or volume. There are very, very few intermolecular forces between particles, and each particle travels at its own speed and direction. There are large spaces between these particles, so only when they're very close together do they experience some intermolecular forces, but for the most part they're spread far apart. And if your pressure is increased, we already know this from our gas laws, if you increase that pressure, or temperature is decreased, particles are forced closer and closer to each other, or they can slow down if that temperature is decreased. Every phase diagram is different. Every substance will have their own unique phase diagram. The strength of intermolecular forces and other chemical and physical properties all affect the behavior of the particles of different substances, and no phase diagram will be exactly the same. There are a couple of points on a phase diagram that have interesting names. So one is a critical point. The critical point is the end point of a phase equilibrium curve. The point defines the conditions where a gas cannot be liquefied using pressure. So here we have a gas. If we want to get this gas to a liquid, one way of doing that over here is just by increasing the pressure. But beyond this temperature, you can't do that. You're no longer going through this equilibrium curve, this boiling curve. This critical point is also the boundary where a liquid cannot be heated to form a gas, going the other way. The fluid then exists at higher pressure, so beyond that, that is called a supercritical fluid. These supercritical fluids have properties of both gases and liquids. Supercritical fluids exist in the high-pressure atmospheres of gas giant planets like Jupiter and Saturn. Another interesting point on the phase diagram is the triple point. The triple point is a set of conditions, a specific pressure and temperature, where you can have gas, liquid, and solid all existing in the same sample. Sometimes the triple point pressure is the lowest pressure at which a liquid of that substance can form. You can see beyond this point, you can't get into this liquid area, right? So that temperature, that pressure. If a sample exists at the triple point and that pressure is increased, so we have to go higher, then you'll transition into a solid, right? Directly up. And if we're starting at that triple point and the pressure is decreased, then we've landed in this gas territory here.